This lesson deals with supplemental problem 315. You can find this problem in the ECE302 ebook in the Chapter 3 Supplemental Problems on page 21. Given this NPN transistor circuit with two resistors and one battery, could you find the base current, the collector current, and the collector emitter voltage if VBE on is 0.7 and VCE set is 0.2, and the beta F can vary from 30 to 100 to a very, very large number, say approaching infinity. This circuit only has one source of power. Current's going to come out of here, go back to ground, back to the power supply, and likewise go back to ground, back to the power supply. Because this is a large resistor, I expect a very small base current, and this is also not a very large resistor, so I won't have a big drop across. I'm going to guess that it's in the active region. Our first step then is to put the model in. Here I've got my 9 volts, 1.5K, 10K resistor, and then from the base to the emitter I've got 0.7, and between the collector and the emitter I've got beta FIB. Because there's IB here and 30 IB here, there's 31 IB here. If I go around this loop, I just have one unknown. 9 volts is equal to 1.5K times 31 I sub B plus I sub B times 10K plus 0.7. I can solve for I sub B. It's going to be 9 minus 0.7 divided by 1.5K times 31, pulling out the IB, and then plus 10K. That's 146.9 microamps, and then it's greater than or equal to 0. The collector current would be beta FIB, and that'd be 30 times this answer, and that's 4.4 milliamps. The collector emitter voltage here, we can solve for by going around the loop. The rise in voltage is the collector emitter voltage. The drop is a minus 31 IB times 1.5K plus 9 volts. That's this expression. Plugging in the 146.9 microamps, I get a minus 6.83 plus 9. That's 2.169, and it's greater than or equal to 0.2 volts, so the assumption checks. If beta increases to 100, we're probably still in the active region. Let's continue with that. All that's going to be different here is that in this equation, we're going to have, instead of 31 I sub B, we're going to have I sub B plus 100 I sub B, so 101 IB. The base current is going to be 51.9 microamps. That is greater than or equal to 0. 100 times that is 5.139 milliamps. And the collector emitter voltage, we're going to solve it. Rise in voltage here equals drops around the loop minus 101 IB times 1.5K plus 9 volts, and now that's 1.21 volts. And that's greater than or equal to 0.2 volts. By increasing beta F by a factor of 3 1/3, the base current went down by a factor of roughly 3 1/3, and the collector current stayed about the same value. Let's take a look at the next idea. Let's let beta get really, really big. Take this equation for I sub B and replace this by its formula of beta F plus 1. If beta F gets bigger and bigger and bigger, this denominator grows, and this value will start to shrink. If you were to take the limit as approaches infinity, which we know can't really happen, this would approach 0. But it's not 0, it's something that's small. If that's true, then the drop across this resistor is going to be a very small current times 10K, roughly 0 volts. The collector emitter voltage is roughly equal to, rise in voltage equals a drop of 0 plus 0.7. The collector emitter voltage begins to approach 0.7 as beta F gets larger and larger and larger. And we're seeing that here. As beta F increased, the value of VCE started to decrease. We're always in the active region because we've got this loop here and there's at least 0.7 volts, and then this is going to be added to the 0.7. With this current being 0, then this current is the same as this one. The value here is going to be infinity times the base current. If the base current's approaching 0, then I have 0 times infinity. If you remember from calculus, that's indeterminate. It actually can take on any value it needs to. In our case, it's going to be equal to the current that's in this resistor, which would be 9 volts minus this node voltage, which is 0.7, and then divided by 1.5K, and that's 5.53 milliamps. And that's going to be the value of 0 times infinity. Our assumption checks. We have a voltage greater than 0.2, and we have a base current greater than 0. What kind of problem is this where we're letting beta approach infinity? Clearly beta F is not equal to infinity, but if we assume that it's a very large number, then what happens is we don't have to solve for the base current. We just assume it's a small number but positive. And that cleans up a lot of the algebra in the problem. In this case, the current in this resistor is very easy to calculate. We get the collector current, roughly the same as the value of I, as 5.53 milliamps. You can see it's approaching that. When beta F was 100, it was 5.139. When beta F was 30, it was 4.4. You get a rough handle on where this current's approaching by making this assumption. It'll get me in the ballpark of the answer. And sometimes if you're doing a test, you could do something that's real simple like this to figure out roughly what your answer should be. And of course, you can do the algebra here and get the exact value given the value of beta F. This technique is really handy when you're doing large integrated circuits, and we'll do some of this a little bit later in the course. And this is supplemental problem 315.